Welcome to the new world.
Boy, I'll tell you. Yeah, it's something. Yeah. Grandkids are going stir crazy.
Are they with you, or do you just know about them?
Yeah, every couple of days they'll be hanging out with us today. And,
Gotcha.
yeah. We see a lot of people walking around the block, that's for sure.
Well, outside is not a bad place to be as long as you keep your distance from others.
Yeah, yeah.
All right, who all is here? I've got Brady, Athos, Brooks, Connor, Karen, Tom, Chase, Grace. Do I have anyone else? Okay. So I'm missing Maddie and Bryce and Steven. All right. Let's get started. First of all, go ahead and turn on your microphones. It looks like a number of you are muted. So first of all, how's everybody doing?
Good.
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 Good. You're keeping socially distant from everyone?
Sorry.
Trying.
Yep.
Good, good. All right. So on the Moodle site, you can see that for today, I posted actually the link to the video. Although if you've been following the videos on the YouTube channel, you know where to go and get those. It's just in the playlist. They end up getting ordered by date. I also basically, let's see, what else? What all was in the Moodle message that I set up? I'm now forgetting. Give me a minute to go and log on to Moodle. Oh, I had two videos is what I had. So one was the walkthrough through the P's analysis that we started the Friday before we left for spring break, and then a separate video on nonparametrics in general and the Kruskal-Wallis test in particular. So whether you get the link from the Moodle site in the description section for today's activities, or whether you just go and check the Moodle site, the YouTube site rather, those videos are up and running. So first question, did everybody get a chance to go and take a look at those?
Yes.
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 Connor, Karen,
What
out
is in
those.
the PowerPoint. I haven't looked at the emails yet.
Who was no? Atos?
Yeah,
Okay, all right. So you need to go and take a look at those. So the way this is going to hopefully work is that I will post those at least a few days before class meets. Think of those things as, you know, homework, just like you would be reading the textbook, etc. And that would be preparation for these times that we spend together. So if you go and look on the Moodle site right now, you will also see on the Moodle site that up at the very top of the course where there was a schedule, in the very first section of materials, you'll see that there is a revised schedule. So over spring break, I basically went through and looked at where we were, looked at what we still had planned, and I've revised the schedule there. In addition to the change in topics, what days they're going to be on and things like that, I've also placed specific readings out of the textbook that will hopefully help you as you work your way through this. In some cases, so for example, on Wednesday, we're going to start two-way analysis of variance. I don't want you to read the first section of the chapter on two-way analyses because it's about nested analysis of variance, which is strangely enough a little bit more involved and harder than just a standard two-way analysis of variance, which comes up in the second section of that chapter. So don't read the section on nested analysis of variance. Skip forward to the next section of the textbook. But anyway, in the column entitled Readings, it should have the actual readings of what sections I want you to read. And the section numbers in there are inclusive. So when I say from section 9.2 to 9.213, it means read section 9.313 as well at the end. I don't recall.
sounds good.
Actually.
Yeah.
Right. So I want to basically debrief a couple of things with you guys today. Do you have any questions about the ANOVA problem set?
Yeah, I have several questions.
Yeah.
So my biggest question is with the Levene's test. I guess I'm not really sure what we're supposed to do with it because I get that it's about like testing homogeneity of variance. But in my notes, I could only find us doing it in R. And so I guess I don't really know how to do it by hand.
Okay. I thought I had gone through this. I don't remember if it was on the 11th or the 13th, but what you do is for each sample, so let's say for the P's example, for each sample, you find the median. So let me pull up the data set. All right, I'm going to share my screen with you guys. So can you guys see my screen?
Yep.
All right, cool. So here's the P's data set, and it's laid out right now in the format that you would have it for doing an ANOVA in R. But what I can do is I can copy, for example, the control. Let me make this a little bigger. So I can copy this data set out like this, and then what I can do is I can go through and sort this. And so now they're ordered from top to bottom. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 values in here. So The median is the middle of the data set. So we would go down 1, 2, 3, 4, 5. So 68 is there and 70 is there. So the median is 69. So then we would just take the absolute value of this minus 69, and that should give you an absolute value of 4. And so these are now all of the medians, and you see that they're all positive numbers because they're absolute values. And so what you would do is you would do this for each treatment, and you would generate a column full of differences, essentially. These are the absolute deviations of the actual data points from the median. And then that column of differences, you just run an ANOVA on. And so that's all a Levene's test is running an ANOVA on the absolute deviations of the data points within samples from the median of that sample. Does that make sense?
Yeah, that makes sense.
Okay, yeah. So I'm pretty sure I went through it on the board, but I think it was the day that the iPad didn't record. So we don't have the 11th, the March 11th lecture on YouTube. But anyway, it's a pretty simple operation. Just convert everything to deviations from the median and then run an ANOVA on that, essentially a new data set that is these deviations.
Okay.
You could do it from the mean, but it'll give you a slightly different answer. And one of the reasons that the Levene's test is usually done from the median is it removes the influence of outliers, because the outliers will tend to move the mean around more than it moves the median around.
With number 4, so will we need to have other numbers than the table gives us to do the ANOVA?
No, you don't.
No, we don't.
Yeah. So let me pull up the assignment so I can see it myself. I went through this in class, but you weren't here because you were not feeling well.
Right.
So let me get some numbers up on my whiteboard real quick so that I can kind of walk you through it. Now this particular question was a little evil on my part. But it's evil because I want you to think about what these things actually are. So we have flex time, we have staggered hours, we have fixed hours, and what I've given you is I've given you the sample size for each of these, which is 27, 59, and 24. I've given you the mean satisfaction, 35.33. Let's see, 31.05 and 28.71. And then I have the standard deviation, which is 10.22, 7.22, and 6 and 9.28. All right, I'm gonna shift my computer to stop sharing the screen. All right, can you see my whiteboard?
Yes.
Is it clear enough?
Mm-hmm.
That's fine.
Okay.
Yeah.
So fundamentally, one of the things that you need in order to calculate an ANOVA is you need what the means are. So it gives you the means. You also need the sample sizes, because sample sizes is where you get your degrees of freedom. The confusing thing is I haven't given you any of the original sample data, but the fact of the matter is you don't really need the sample data because the problem gives you standard deviation. What is standard deviation? What's the formula for standard deviation?
Oh,
Square root of sample variance.
Square root of the sample variance. Who was that?
Brady.
Hey, Brady. Thanks. So if we want to get the sample variance, what do we have to do to standard deviation?
Square it.
We just have to square it. So if we square that, it will return to us the sample variance. And what's the formula for sample variance?
So-
X minus average squared divided by n minus 1.
So it's the individual data minus the mean squared summed up divided by n minus 1. In order to calculate an ANOVA, what's the first thing that we end up calculating? We calculate the mean, but then what's the next thing after that?
The sums of squares, right?
Okay, where are the sums of squares?
Among.
What's that?
Sum of squares among.
Okay, so we can do sums of squares among pretty easily. I'll show you how to do that, but what about sums of squares within? Where do sums of squares within exist?
Each sample mean and then the individual sample points.
So it's in the numerator of within sample variance. So if we can get within sample variance, we know what the numerator is if we just multiply this times n minus 1. N minus 1 cancels, and you're left with the sums of squares for that particular sample. So take the variance, square it, multiply it times, in this case, 26, and that should return to you the value that is the sums of squares within. Once you know sums of squares within for that particular sample, the sums of squares within for the entire ANOVA is just that added up across all three groups that you have here. So you can calculate sums of squares within that goes into the ANOVA table just by knowing what the standard deviation is. How will we go about calculating the sums of squares among?
Find the grand mean.
So the first thing you have to do is you have to find the grand mean. The grand mean is going to be the weighted averages of these averages. So this times 27, that times 59, this times 24. Add those values up and divide by the total sample size. That's then the grand mean. So it's the sample size of the first sample times the mean of the first sample plus the sample size of the second sample times the mean of the second sample plus the sample size of the third sample times the mean of the third sample. That whole thing divided by the total sample size. That's the grand mean. Once you know what the grand mean is, you know how to calculate sum squares among, because it's once again the weighted deviations from the mean. The weighted deviations of each sample mean from the grand mean. That's sums of squares among. So knowing this tells you what sums of squares within is, and knowing these two things allows you to calculate what the sum of squares among is. And that's all you need to do an ANOVA, because ultimately the ANOVA is just the source of the variation, the degrees of freedom, and the sums of squares. These are all the things that you need. The source is, what type of schedule you're working with, and then the residual variation that's unexplained by schedule. You know what these degrees of freedom are because they're all in the table here. You know what the sums of squares is because you can calculate this, and you can calculate the grand mean from that. Grace, does that help?
Yeah, so for the within, you will take the variance, you square it, and then you'll sum that across, like down the column.
Nope, you have to take the variance and square it, and then multiply it times the sample size minus 1 to you're trying to isolate the numerator of the variance.
Oh, okay.
So you have to do that individually for each sample, and then you add up all the samples.
Okay.
So the reason I put this, so there is a reason for this question being in the problem set. I want you to always be able to relate back to the earlier things that we studied, which were fundamental things like, what is sample variance? Well, sample variance is the sums of squares divided by the degrees of freedom, which basically means that variance is essentially a mean squared. Because in an ANOVA table here, the next thing we calculate is the mean squared. Now I'm going to have to erase some things. The mean squared is just the sums of squares divided by the degrees of freedom, which is exactly what the variance is. The sums of squares divided by the degrees of freedom. So when we use the term mean squared, we're basically talking about one type of variance. In this case, it's the variance among divided by the variance within, which gives us the F statistic. So when we talk, I think at the beginning, I talked to you guys about how we call it an analysis of variance rather than an analysis of means, because it's really just an analysis of different types of variance. Variance among means versus variance within means. But the thing that we're comparing is always an estimate of a form of variance. Does that make sense?
Yes.
Okay. Anybody else have questions about that? Anybody?
Nope, I don't.
All right. Okay, what other questions do you have about the problem set?
I have one.
Yeah.
How are you supposed to do the post hoc analysis without using R?
So the post hoc analysis is based on, let me go pull up a PowerPoint for you so that you can see it. Can you see my screen now?
Yes.
Okay. I'm going to scroll down to where we covered this. So in the PowerPoint that you have access to from the Moodle site, let's see. Trying to figure out how to make my screen bigger. You see that that this is the equation here. So what you have to do is you have to calculate the minimum significant difference. And what you use is you use this critical value Q, which I showed you in class. You can go and look up their online calculators for. This thing is oftentimes referred to as the studentized range statistic. So if you just type up studentized range statistic calculator, it will send you to a place where you can calculate this online. And so to calculate what that is, what you need is the standard error of your sample. And the standard error is calculated by taking the mean squared within times 1 over the sample size of sample 1 plus 1 over the sample size of sample 2 divided by 2 and taking the square root of that. That's what SE is. And then look up the critical value on an online critical value for the studentized range statistic, which is Q, where K is the number of treatments and V is the degrees of freedom for the mean square within. So recognize that you're using the mean squared within, not the sum of squares within, but the mean square within. Once you have the mean square within, which you already had to calculate to do the ANOVA in the first place, all you really need is Q and the sample sizes of the two samples that you are comparing at the moment. So if you have sample sizes like in the P's analysis where each sample is the same sample size, doing the sample size is easy enough. If you have samples where sample sizes are different, for a given comparison, you have to adjust the sample size, and that's going to change slightly the minimum significant difference. So if you've done the ANOVA, you have everything you need to know to run the Tukey-Kramer test, with the exception of this Q statistic. Once you calculate the minimum significant difference, if the difference that you observe is greater than that minimum significant difference, then that's a significant difference. If it's less than that, then it's not. So it's very much a either or. You know, once you cross that boundary. So you need the alpha level, you need the K, and you need the V, where alpha is 0.05, K is the number of treatments, and V is the degrees of freedom for mean squared within. And I can maybe. Let's see, how do I get out of this? Let's see. Oh, there we go. So let's go to the internet and go to studentized range statistic calculator. Can you still see my screen?
Yes.
Yes.
Yeah, so number of means for the P data was 5. The degrees of freedom was 45. Oh, that's actually doing the wrong thing. Q-crit is what I want from Vassar stats. So the number of means being compared was 5. The degrees of freedom was 45. And when you click calculate, it gives you 4.02, which is where I got this 4.02 that is in my PowerPoint. So I got that from a Q calculator at Vassar Stats. And there's a table actually in the book of statistical tables that I have that sits in my office that I sometimes bring to class, but it only goes up to 24, and then it starts making jumps of 10, and so you have to extrapolate, which I don't feel like doing generally. And so the easier way to do it is to just look it up online. So if you know what Q is, you calculate what SE is based on the mean squared within and the sample sizes of the two samples that you happen to be comparing. And then what that gives you is it gives you a table like this. Now, once again, for the P's analysis, all of these minimum significant differences are the same. Can you see the table that I'm showing you?
Yeah.
Yes.
So all of these are the same. And you basically ask, okay, if I'm comparing control to glucose, whoop, go back. If I'm comparing glucose to the control, this is the minimum significant difference. Well, what's my observed difference? The difference between glucose and control was 10.8. Because 10.8 is a way bigger difference than 2.97, we would conclude that that one is significant, which is why it's highlighted in red. Same thing for control versus fructose. We look at the observed. What is control versus fructose in the minimum significant difference? 11.9 is greater than 2.97. And so once again, we would conclude that that is a significant difference. The ones that are in red are significant. The ones that are not in red are not significant because they're all below 2.97. Now, if control and glucose both had 10 sample sizes of 10, but control and fructose had different sample sizes, the minimum significant difference for fructose control would be a different number, but you would compare this number here with this number here and see if those are different. So sample size does matter in that it can change what the minimum significant difference is for any particular pair of samples you're comparing. So if we go back, and you could do this for practice, if we go back to the tick data set, where we have different sample sizes of each one, if we're comparing host 1 to host 2, we have 8 values for host 1 and 10 values for host 2. When we go and calculate the standard error for calculating the minimum significant differences, it would be 1 divided by 8 plus 1 divided by 10 multiplied times the mean squared within. So that would change that minimum significant difference for that particular comparison between host 1 and host 2. It would be a different minimum significant difference for host 1 versus host 3. Does that make sense?
Yes, perfect. Regarding
Okay.
homework, do you want us
Yeah.
to send to your email, your Jewel email?
Yeah, so 4 of you have already sent it to me. Just send it to my email. In, I think, every case that I've gotten so far, it's just basically been Microsoft Excel spreadsheets that basically show me what the calculations were that you did. And so, yeah, just attach that. And if you need to add any comments to it, you can put those in a document and send me a Word document. But I've been able to follow people's work pretty well just looking at their Excel files, because I can actually see what your calculations are.
Okay.
Yeah. So Tom had some questions. Actually, Tom had questions about the Tukey-Kramer test, the Tukey honest significant difference test. And by being able to look at the actual equations, I was able to figure out what he was doing wrong and sent him an email saying, hey, fix this part and it should work. And then he did, and it worked. So.
So for the post hoc test, do we only do that whenever we find that the ANOVA or the like the F statistics are different from each other?
Yeah, so your initial test of the F statistic is whether the overall ANOVA is different. And what the overall ANOVA is telling you is that at least 2 of the means are different from one another. It doesn't tell you which ones. Back before we left for spring break, Connor came by my office and he's like, so we did an F test and we figured out that something's different. That's kind of unsatisfying. I'm like, yeah, it is kind of unsatisfying, because if there's something different in there, you kind of want to know what it is. Give us a day and we're going to get to that. And then we did. So you only want to do any sort of testing among means if your overall ANOVA is significant. If your overall ANOVA doesn't show any differences, it's pointless to then go and look for any pairwise differences, because in theory they don't exist.
Mm-hmm.
So yeah, you have to have a significant overall ANOVA.
Okay.
If you don't see a significant overall ANOVA, you're done. It's whatever the categorical variable that you were using to organize your data is, that categorical variable doesn't matter, essentially.
Gotcha.
Yeah. So then there's no reason to go looking for reasons that it might. Other questions?
So I just wanted to confirm. So on some of the questions it asked for both the Levine's test and a Shapiro-Wilks test, but I thought you said in class that like the Levine's test was kind of a replacement for the Shapiro-Wilks test.
No. Levine's test is a test for homogeneity of variances. The Shapiro-Wilks test is a test of normality.
Okay.
And it's a test that we talked about way back at the beginning of the semester.
Yeah.
When we were talking about distributions.
Yeah, I was on the exam.
Yep. Yeah, it was on exam 1 material, which is the only exam that we have. Yep. So what I would do for all of these data sets that you're working with is I would basically calculate the residuals for each sample. So the residual is, once again, you can see my screen behind me. The residual is just the data point minus the mean without squaring it. So it retains positives and negatives. So a distribution of residuals, if it's normal, the residuals will be normal. And because you're combining all of the residuals across all of the different treatments, they will all be centered on 0. There will be some positive residuals. There will be some negative residuals. But by calculating the residuals for each sample and then combining them into one big data set, you have a lot more power to detect differences from normality than if you're just doing it on a sample size of 8, for example. So I would calculate each residual individually. You don't square it. That retains the sign, so you have positive and negative residuals, and then do a Shapiro-Wilk test on all of those residuals for the entire data set.
Okay, yeah, that makes sense. Do you want us to graph it like that, like in a histogram?
Oh no, you can just have the calculations.
Okay.
Yep. You can in R make a histogram of it, and I show you how to do that in the PEAS walkthrough. But yeah, you don't need that for homework.
Okay.
All I need is a W to know that you got the correct Shapiro-Wilk statistic, and then that tells me that you got that. If I see anything looking hinky about that, I'll go back and I'll go through and I'll dig into your calculations and make sure. Now, once you have all those residuals, remember you have to rank those residuals and then go and get, go and find a Shapiro-Wilkes table online, or you can email me, and I have the Shapiro-Wilk test tables in my manual of statistical tables. And I'm less concerned that you know how to calculate the Shapiro-Wilk test because you've already done that in a problem set before. So if you wanted to plug in the Shapiro-Wilk test in particular into R and just calculate it that way, I'm fine with that, because that's the least important of all the things you have to do in association with an ANOVA. But what you're going to find with all of these samples, all of these examples that are in the problem set, is they're all not significantly different from normal. So, but it's always a thing you want to test. And so you'll see in the PEAS analysis that I have, I load in the data, I look at the data to make sure that the data are correct, and then the next thing that I do is I test for normality and I test for homogeneity of variances. And in the PEAS example, the homogeneity of variances thing is a little wonky, and the transformation that I use is a transformation that I got out of the textbook that had this as an example, and it is not a transformation of the data that I would have arrived at had I been left to my own devices. There is a section in your textbook on transformations, and I think my textbook is at my house. Anyway, just look up transformations. It's around page 62, I think, in the textbook. And it talks about transformations, the standard types of transformations that you can use for doing things like stabilizing variance. The transformation that I use in the PEAS example is not one of the standard transformations for dealing with homogeneity of variance issues.
Okay, but we only need to do that if the Levene's test is significant?
Yep.
Okay.
Yeah, because you're basically doing an analysis of variance on the deviations from the median. So If you have differences from sample to sample on the size of those deviations, then obviously you have variances that are different. Because it's just an ANOVA on those deviations.
Dr. Klawinski.
Yeah.
So for example, if we have like a huge difference on our values on the Shapiro-Wilk test, do we need to have also an ANOVA table?
Yeah, so your Shapiro-Wilk test, are you talking about for the problem set or for the Gecko write-up?
I mean, more in general, I mean, if I'm analyzing a data set and I run a Shapiro-Wilk test on that data, and I got like a huge different number from the table one, is it valid for me to have another test, which will be the ANOVA?
Yeah, so what the Shapiro-Wilk test is doing is it's testing one of the assumptions that allow you to be able to do an analysis of variance. And so in theory, before you proceed to doing an analysis of variance, you should do something to your data to make your data more normal. That's why that section of the textbook dealing with transformations is important. So let me erase something. I had an eraser just a little while ago. What did I do with it? So, can you still see the whiteboard?
Yeah.
Can you see the, all right. So a really common kind of deviation from normality that we see is the case of skewed data. And oftentimes we see positive skew. So a distribution that looks like this. And this is the distribution that we're taking our initial samples from. And as a result, when we go and test the data, a bunch of our individual observations of data will be down here, but then you will get the occasional data point that is from this tail. And when you go and test those for normality, you're going to find that your data are not normal. Well, one of the cool things about this, so a common way to solve this problem is if you take the square root of the x values, it doesn't really change these low value values very much, but it takes these big values and basically takes the square root of them. So the square root of 1 is 1, whereas the square root of 100 is 10. So if this was 1 and this was 100, it basically brings this value in and puts it at the 10 spot by taking the square root of it. And so it takes this distribution and it essentially pulls the tail in. At that point, then your data are more normal. And as a result, you don't violate one of the conditions of an analysis of variance. And as a result of that, you can then proceed to doing the ANOVA. Another useful transformation for this is taking the logarithm of the value. That also tends to pull that tail in and make data that are positively skewed more normal. Now, there are times when you get a significant Shapiro-Wilk test saying that your data are not normal that you want to ignore. And an example of this is the Gecko data set that we'll talk about here in a few minutes. So yes, your ultimate goal, Athos, is to be able to do an ANOVA, but you have to check the assumptions of the ANOVA first to make sure that the answer that you get out of the ANOVA is an answer that you can trust. Does that make sense?
Yes, thank you.
Okay. When you don't meet the assumptions of the analysis of variance, one of the things that you can use is a non-parametric method, which is what I introduced to you in the PowerPoint that was intended for today, which is a non-parametric analog of the analysis of variance test. And I just found my eraser. All right, what else? Other questions?
Should we have used data transformations in the problem set, or should they
No.
have? Okay.
No, because all of your problem set questions have normal data and have homogeneous variances.
All right, then I must have done the calculations wrong. Thank you.
Yeah.
Yeah.
Yeah, I checked them before I ran all of the problems in the problem set to make sure that they weren't complicated from that perspective. Because once again, I'm more concerned in you knowing the mechanics of doing the ANOVA than I am that you know the mechanics of testing the assumptions. But it seems that you are miscalculating, and it might be that you were not doing something correct with medians of the using medians for your calculations for Levine's test, or I'm not sure. I would have to look at your work to see what the issue was. Any other questions on the problem set? All right, let's talk about the Gecko temperature data write-up. How is that going for everyone? All I hear is silence, which usually in a classroom indicates to me that you haven't gotten to it yet.
Correct.
That is correct for me.
Okay, I just want to take you through something that you will encounter. I'm going to share my screen with you again. Hey, Tom, are you there? Tom.
Yes. Yeah. Unmuted.
Yeah. Unmute yourself.
Yeah.
Would you feel comfortable taking students through, because you and I have already had the conversation about this.
All right. Yeah.
So just to help them through this process.
Yeah. Let me pull up my stuff.
So I've got R in theory somewhere. Oh yeah, there we go. So I'm going to share my screen with everybody, and so Tom emailed me last week about the Gecko temperature data set. Can you guys see my screen?
Mm-hmm.
Yeah.
Jesus.
So one of the things that you will find when you go through the Gecko temperature data set is that the Shapiro-Wilk test will tell you that your data are slightly non-normal, very, very slightly. It's like 0.047 or something like that is the p-value. But then you'll run the Levine's test, and the Levine's test will tell you that your variances are not similar at all. Not only are they not similar, the p-value is like the minimum p-value that R calculates, which is like 2 times 10 to the minus 16th or something like that. They're ridiculously non-normal.
In fact, if you guys want to write this down, the F value was, for me, was 9.767. So there I am sitting with the Levine F value that's like really high. So I'm thinking this must be one of those cases where I need to transform it. So that's when I emailed Paul.
Yeah, so then walk them through what I showed you and what I told you, because what I showed you is on the screen, and then tell them what I kind of went through with you.
Let's see. Well, I'm having a little trouble with my screen. Hang on. Let me find my. Okay, so I got this high Levine. Also, when I did the Shapiro Wilks test, it was slightly off too. And for a number, if you want to write this down, the p-value I got was 0.047. So it was just under that 0.05. So both of those were not fitting. And so I tried that transformation that we saw, excuse me, in the P thing, and that just made it totally worse.
Which is not a standard transformation.
Yeah, I found that out. Yeah, and so then I guess that's when I called Paul, because I was trying to kind of do this transformation by myself, and it just headed in the wrong direction. So then Paul referred me to an article and some stuff. I guess I'll let you.
No, I want you to do it.
Okay. There's some article by Zimmerman. I don't know if, Paul, you're going to post that or not, but it shows that parametric tests are less biased. They apparently don't have a bias when you got both normality and your variance issues violated. Parametric tests actually don't have that much bias.
Well, they have less bias than non-parametric methods. So
right. Yeah.
What you would usually go to in this instance is you would go to a non-parametric method, but it turns out that non-parametric methods are generally weaker in terms of their statistical power and can be biased just like a parametric test is. But when you violate multiple assumptions all at once, the parametric methods are less biased than the non-parametric methods. What else did I tell you?
So that to me was all around good news, because then I could just not have to shift to non-parametric, because we really hadn't learned that yet, and could just continue on with untransformed data.
So whenever you are confronted with a violation of one of the assumptions, my advice is to create a plot of the data. So on your screen, if you're looking at the screen share that I have, you'll see that I've made a very preliminary plot that shows you the means and the 95% confidence intervals, but it also plots all of the data. And what you see is that for Summer Galveston and Summer Oklahoma City data, the means are very similar to one another, and their 95% confidence intervals are fairly narrow. And then the temperatures go down as you go to Winter Galveston and Winter Oklahoma City. But the variances increase in those two compared to the summer data, but they're not shockingly bigger. So if I go up here and plot the confidence interval plot data frame that I created, you see that the confidence interval only goes from 0.3 to 1.1, and this is in temperature units. And so the 95% confidence interval for the biggest one spans about 2 temperature units. But the difference between the summer temperatures and Galveston, Oklahoma City is a difference of about 5 degrees when you look at 30 versus 25 here. And the difference between those summer temperatures and the winter temperature in Oklahoma City is 15 degrees. So one of the things that you always want to do is you always want to make decisions about what to do based on the data. And so even though these variances are turning out to be significantly different when you conduct a Levine's test on them, they're not so drastically different that it obscures your ability to make a decision about whether means are different, because the differences in means are way bigger than the differences in the variances. And so when you look at those data, you can pretty much say without too much problem that those winter temperatures are different from the summer temperatures, and winter in Galveston is very different from winter in Oklahoma City. And so at that point, you can say, well, let's have a little faith in the central limit theorem, in that these things are normal and are going to have relatively similar variances. Because why are we able to find these differences among variances when we look at these data? What's the reason that we can tell that these small differences in variance are significant? This is not a rhetorical question. I expect you guys to answer.
You said, what's the reason why we can tell?
Yeah, why can we detect these small differences in variance?
Because we have a large sample size.
Yeah, we have sample sizes of 52, 60, 30, and 40. So we have a lot of power to detect really small differences. So when you think about p-value, and we haven't talked about criticisms of using p-value as a criterion for making decisions, but when you think about p-value is as much about sample size as it is about differences among means. If you give me enough time and enough money, I can show you that any teensy-weensy difference is significant using a p-value because I have gigantic sample sizes. So you always want to exercise judgment when you're using something like a p-value to decide whether or not, in this case, you have a problem with an assumption, or even when you're detecting whether means are different. Because simply because you have a high p-value, or a low p-value rather, a low p-value doesn't necessarily mean that that difference is a difference that you should be paying attention to. That low p-value may just be due to the fact that you have gigantic sample sizes. And so this is one of those cases where you see a significant Levene's test telling you that your variances are different, but relative to the differences among the means, those differences in variances are actually pretty small. And so what was my advice to Tom?
Just continue on with untransformed data.
Yeah, continue on with untransformed data, because I tried a number of transformations and all of the transformations just actually made everything worse using the standardized kind of transformations that are found in your textbook. Now, what that means is when you do your write-up, you have to issue some caveats that basically say, we found that this was the case, we looked at the data, then based on the data, we proceeded without doing the transformation, which means that the reader should always, have that in the back of their heads as they're interpreting your conclusions, but you've been transparent about what you did, why you did it, and you've signaled to them that they need to be aware of this as they read the results.
So in the profession of statistics, we had samples, like we had 30, and then the smallest one, the largest one was 60. So those are considerable when we're looking at those.
Yeah, for most statistics, those are pretty big sample sizes.
Okay.
You consider the fact that when molecular biologists do work, oftentimes they have sample sizes of 3 or 4. Yeah, these are all substantial. Notice also that the size of the standard deviation is roughly correlated with the size of the sample size. So standard deviation here for a sample size of 30 is 3, for a size of 40 is 2.4, for a size of 52 it's 1.25, and for a size of 60 it's 2.1. So there's this correlation between the estimate of the variance and the sample size. And of course, that comes from how you calculate what a standard deviation is or what a variance is. It's all involves dividing by sample size. But getting back to maybe a question that was underlying your question that you just posed to me, is this issue of when you're doing statistics, you can cling tightly to the p-value and say, oh, the p-value is this, therefore I can't do an analysis of variance. But there is some judgment, but your judgment should be involved in looking at the data and saying, okay, these data look a little skewed because looks like there's more on this side of the mean than on this side of the mean. This has just got a little tail to it. This has a little tail here. This is way more spread than this one is. This one has these three outliers, et cetera, et cetera. These three outliers, though, should, if anything, be pulling this mean towards the other means rather than away from the other means. So these three outliers should obscure differences rather than reveal differences. These outliers should be pulling this mean downward, once again, obscuring differences rather than revealing differences. So there's quite a lot of judgment that goes into doing statistics and doing statistics in a realistic and well way rather than just a robotic. I ran the test in R, it gave me a p-value, and I did nothing after that p-value because I had a significant differences in variances. So it's always good to plot the actual data. And then make a decision about where you go next after you've looked at it. Does that make sense? Everybody there?
Yeah.
Yep.
Okay. All right, other questions about the write-up? There is a sample write-up on the P's analysis that I've written that is kind of the way that I want you to format everything and the way I want you to approach everything. It's on the Moodle site. Go and look at it. It's in the same folder where the assignment is. So definitely read that before you start writing your own.
Wait, that's in the same folder as the report?
Should be. Let's see, did I not put it in there? I thought I put it in there all at the same time. Let me go and look on the Moodle. Yeah, if you click, son of a bitch, it is not in there.
That's under March 13th.
Is it under March 13th?
I think it's in the P's analysis materials folder.
I think it's in both, yeah.
Where it has like the screencast in the R script and data file, like for the P's. Oh yeah, and the sample write-up, perfect. Yep, it's up.
Yeah,
Yeah, it's there.
15.
Yeah, it's on. It's in the thing called P's analysis materials, which is March 15th to March 21st. So here's a screencast of the updated R script. Also a sample write-up. Yep. So it's in this. It's in the folder called P's analysis materials. During the week that technically we were on spring break. So yeah, so hopefully that will help you with that process. All right, we're almost out of time. Some of you haven't seen the non-parametrics write-up or the non-parametrics PowerPoint, so I want to, I guess, give you time to look at that. probably right after I do this, I'm going to create a screencast introducing us to a two-way analysis of variance, where we have two categorical variables that form groupings of our data. So on Wednesday, I want to go through the non-parametric stuff, which is pretty quick, and then start on two-way analysis of variance. Question?
All right.
Just to
Sounds good.
confirm, the problem set is due at 5, right?
Yep, sure. I think, is that what I said? Yeah, well, we can just make, one of the things that was suggested to us is just to make standard kinds of due dates for things. So we'll just do due dates for everything that's due from here on out. Will just be 5 o'clock that day, like close of business that day. It was suggested to us that we make standardized cutoff times for when things are due. Some people are doing midnight, etc. But basically, if there's an assignment that's due for this class, it's just 5 o'clock the day that it's due. So.
Okay.
So could we turn in a revised one if we've already turned one in still?
Yeah, sure. Just let me know that it's the one that you want me to look at.
Yeah, we'll do.
Yep.
So for Wednesday, we'll have a video to watch, and then looks like there's a section in the book under the reading.
Yeah. Yep.
Okay.
And that section, so the second portion of chapter 9 deals with regular factorial two-way analysis of variance, which is where we'll start. Don't read the first part of that chapter. It's just going to confuse you.
Okay.
I don't know why they started with the hardest analysis at the beginning of the chapter. So, all right, last question for you is, did this work for you? Is this going to be a method of doing class that's going to work?
Yeah.
Yeah.
Yeah, I think it will.
Yeah, it's good.
Yes.
Okay. All right. It's crucially important that you guys look at the materials beforehand. Otherwise, we're just kind of sitting here, me trying to deliver a lecture on my whiteboard in my office, which probably isn't the best way to go about doing things.
Right.
All right. Well, cool. I'm glad to see that you guys are all safe and healthy. And I'll see you on Wednesday.
You as well.
Hey, thanks, Paul.
All right. Thank
All
you.
right.
Thank you.
Yeah.
Email me if you have questions.
Okay.
All right.
All right. Talk to you
Okay.
Wednesday.
You guys.
All right.
Okay.